I think I should start admitting them now. Okay. Rashika is going live meanwhile. Okay, we are live, guys.
Hello, all. Very good evening to all. We welcome all of you to the IBM Skills Build Bootcamp. Let's wait for another 2-3 minutes. We will start by 5:05. So please inform your friends to join as soon as possible. So welcome once again to the session. Today we will start the first masterclass. So please inform your friends and colleagues to join as soon as possible. Okay, we will start in 5 minutes. Hello, dear friends. So welcome once again to the IBM Skills Build Bootcamp, Generative AI from prompt to production. So we'll start our session soon. This is the first masterclass. I welcome once again to the first masterclass and kindly request all of you to inform your friends to join as soon as possible. So we'll be directly going to the session today. So likewise, we have already informed you, already given you the timelines and everything. So this is a 2 weeks of boot camp. The first week we'll be having the master classes. We'll be having 3 master classes starting with today. And also along with that, you have to complete your first deliverable, self-learning week deliverable in this week. So you have to submit the first deliverable by 28th February. I think all of you have started. By the time we will be sharing you today, we'll be sharing you the domain ID and password. Domain ID and password is something different. You will be getting a different, access to a different, you'll be getting access to a different IBM cloud. For that purpose, we have allocated you a new domain ID and password. So we'll share the details after this session. And then the second week, you will be working on a project. So you have to submit the project by the end of the 8th March, right? Now today, we have Mr. Amit Tiwari with us for taking the session. He is a very experienced trainer. He is an expert specialized in artificial intelligence consultancy. He holds a bachelor's degree in electronics and with a special focus on artificial intelligence. And he has a very diverse career spanning from digital marketing and the hospitality sector. And he has taken a lot of session across the country, and I think some of you might have attended his previous classes. We had a lot of audiences across India for the Amit Tiwari's classes. And so far he has taken more than 250 plus classes across India, and he have trained more than 15,000 students. And he also served as a guest lecturer in many colleges across the country. So I welcome Mr. Amit Tiwari also to the session. Along with you, once again, I welcome all the students to have a wonderful learning experience throughout this session. Amit, I'm glad to welcome you once again to this session. Over to you.
Thank you so much, Anil, for the introduction. I'll be starting shortly. I'm waiting for some more students to join. Maybe take 2 or 3 minutes, and then I will begin my session. Thank you so much, all 670 participants from you joining it on time. Huge congratulations for taking a step towards your learning journey. I just wait for 2 more minutes, and I will start the session.
Samit, just give me 2 minutes. I just got a few queries from the students. Let me answer in between. Some of you have just texted like that you haven't seen any option to download the certificate, guys. So my dear friends, once you complete the activity, once you complete the large language model, then in the first page itself, if you are logging from the laptop, then you will see probably from the laptop to desktop, you will see there is an option in the front page. In the first page like that, view, there is an action. View action, there is a tab called view action. So if you click on that, you will be seeing that option, view completion certificate. Usually it takes some time to reflect the certificate. And if you're logging from the mobile phone, then once you log into once you click on this LLM page, then on the right side top there is three dots are there. So when you click on the right side three dots, you will be able to see the view completion certificate, and you just need to take the certificate. So I will do one thing after the session. At the end of the session, once the Amit completes the class session, concludes the session, then I will log into the system and will show you how to download the certificate. Okay. Then again, yes, some of you have downloaded certificate. Very great, very good. So if you have any doubts regarding that one, definitely we will assist you after this session. Okay. So by the time, let me ask you one thing. How many of you have completed? Can you just raise the hands, or can you just put in chat how many of you have completed the first assignment? I mean, first section of the assignment. Yes, I can see many students are, many students says that they have completed the assignment in the chat. Great. So, deadline, guys, we have already said you have to complete all your, deliverables by the self-learning week deliverable. That means whatever assigned on you on the IBM Skills Build platform by the 28th, by the end of this week, 28th February, right? So I will share the rest of the details by the end of the session. All right, over to you, Amit. Thank you.
All right. Thank you so much, Anil, for the introduction. Anil will help you in your queries. Hello, everyone. Welcome one more time to IBM Skills Build um, Masterclass Bootcamp on large language models. And we are seeing tremendous success in the large language models in the past from India as well. If you have been looking at the news, then Sarvam AI has launched its large language model recently in the AI Impact Summit that was held in Delhi, and that is a significant development from the past that we Indians did not have a large language model. Now we have one. What we are going to cover in this masterclass and bootcamp is going beyond large language models, learning about generative AI and how we can design our own large language model from scratch as well. So if you are enthusiastic in learning how to build your own large language model, just like Sarvam AI did, we are here live to teach you that. With that, I have designed some slides for you. Today's session will be a quick primer of generative AI and large language models so that we recall some concepts, we kind of like clear some of the notions behind the large language models, and maybe we have introduction to large language models as well. So I'm going to quickly share my slides, which I have designed particularly for you. If you are coming from my previous sessions, maybe this kind of like would look like a repetition of what we did in my previous sessions. But if you are attending it fresh, it would look like something which is exciting and which we are going to cover in the next master classes as well. So we are going to start and design our own large language model from scratch. That means that we are going to train our large language model with code in all of this bootcamp. And by the end of this bootcamp, you will have a large language model of your own. Maybe it will not be as better as ChatGPT or Gemini or Grok. Nonetheless, it would still generate text, and it would still generate some of the text that we will fine tune and train it on. So we're going to train it on some of the text that we will scrap from internet. We will make a corpus and then we fine tune it according to our needs. I'm really excited to take these master classes for you. I hope that you are too. And let's dive deep into the world of large language models. All right, I hope that you can see my screen. This is first masterclass. This is a primer, and I welcome you all to the world of generative AI and large language models. So let's start quickly with what is generative AI. I think we are past what is artificial intelligence, and we all know what is AI, and we don't need to cover that as much. I hope that you all have used ChatGPT, generative AI, some or the other form. So we will dive deep into the deeper concepts of generative AI, what it does, how can we make our own Gen AI and large language model, instead of going into boring details like what is artificial intelligence, why do we need large language models, and what does it do. So what is generative AI and why we have been talking about this in the past 4 to 5 years? So I recall my time when I was learning AI back in 2014. I am an electronics graduate with artificial intelligence as a specialization, and we were doing in 2014 only two tasks, regression and classification. So basically we were learning about machine learning, and there was no notion of large language models, although we had some language models there in 2014 as well. But GenAI was not that popular. And we as academicians and researchers, we thought that we will never be able to crack the code of teaching a computer language. But that's the beauty of technology, that it grows so fast that we are at a phase where computer can not only understand language, but it can generate far better language than humans can do. So let's dive deep into what is generative AI. And generative AI consists of two terms. First one being generative and the second one being AI. So generative means creating new content like audio, code, image, text, and video with the help of artificial intelligence, right? So previously also we could generate or make text, audio, code, image in computers, but we could do that by either typing or maybe kind of like writing the code ourselves, maybe designing the image in some image processing software like Photoshop, Illustrator, and something else. And video, we might be making it in Premiere Pro or some other software like DaVinci Code or something like that. So what changed? And what is exciting in generative AI is that it creates new content. It's not old. It's not been created previously. It generates this fresh content with the help of artificial intelligence, and that's what generative AI is. And we are not very early, or it's not a technology that we designed very fast. We have seen instances of generative AI earlier as well. So we have seen generative AI in Google Translate, where you must have used Google Translate to translate from one language to other language. Here in this case, I'm translating this very famous ad that you see on television. Mutual fund investments are subject to market risk. Read all schemes related documents carefully. And what they did was they did a Google Translate of that, and the translate came out to be mutual fund nivesh bazaar जोखिमों के अधीन है, which was kind of like funny because it doesn't make any sense. The first sentence itself, like mutual fund nivesh bazaar जोखिमों के अधीन है, it's kind of like a very complicated Hindi. But nonetheless, they ran these ads for no matter God knows how long, and we still see the same ads. So that's kind of like a classical case of generative AI, where we were able to generate language, basically translation of one language to other language. And Google Translate came back in 2005, and it's not very sudden. We see the emerging of the language models after 2022 when ChatGPT launched its model, and since then it's being a very amazing ride where we could generate all these amazing things with large language models. But we have seen generative AI prior as well, where we could see instances like in Google Translate, which we started back in 2005. Also, we have seen generative AI prior in Siri, Alexa, and Google Assistant. I know that you must have said at one point of time in your life, "Hey Siri, Alexa," or "Okay Google." And Google launched its Google Assistant back in 2011. So it's been like more than 15 years that we have been advancing in generative AI. So what it generates, it generates a response in response to whatever prompt that you give to it. So the prompt used to be an instruction like, "Hey Siri, set me an alarm for 6:30," and it will generate a response like, "Your alarm has been set for 6:30." So it could do some of the tasks like tell you a joke, or maybe kind of like set up your alarm, or maybe call someone. But yeah, generative AI was there since 2011 as well. It was not that much advanced. It could not generate new content, but nonetheless, it was able to understand human language, as well as it was able to generate text. Another instance of generative AI that we have seen earlier is in language modeling. So language modeling has been there around since 1980s, and we always wanted to kind of like predict the next word in the process. So here in Google, if you type "I want to," we were able to predict the next words in the sentence, like "I want to play games," "I want to break free," "I want to learn," or "I want to sell my phone." So right now here, it is kind of like predicting the next words that might come after "I want to." And similar cases you must have seen in your phones as well, where if you type in "please send me an," it will kind of like try to complete it with "email updated and update." So this was a case of language modeling where we were trying to predict the next token by search and count methods. So we were counting how many types a user must have typed "please send me an email," and then we are kind of like using probability to in order to kind of like predict the next word, which if you talk about maths, it's PWT, my T plus 1, given that WT has already occurred. So it's kind of like using the Bayes theorem in order to predict that, okay, one event has already occurred, what will be the next probability of that event. So we're counting number of times I play must have come after "I want to," and we are counting the number of instances that "I want to" has occurred in the whole language, and we kind of like calculate it and give it a score, and then predict the next token in the sentence. Generative AI now has, there are many apps. This kind of like looks like an old PPT where there are only few apps which are there, but there are many more different apps that are there. We have Sarvam AI from India as well, OpenAI's ChatGPT, Google's Bard, Anthropic's Claude, We also have Midjourney, which can generate images, Quillbot, which can rephrase your sentences. We have Meta's Llama models, Grok from X, and many, many, many more. So we talk about generative AI. What can it do? It can generate text. It can generate text from natural language, particularly anything that you can think of, like essays, resumes, articles, blogs, posts, poems, stories, recipes, instructions. It can also generate image like posters, images, paintings, logos, and icons. It can also generate code like in Java, Python, C, C++, HTML. It can also generate audio like instrumental music, sounds, background score, etc. And also video generation can also be done with the help of generative AI. Right now, we are only able to generate small clips, but in the future, we will be able to kind of like generate many, many sophisticated full-size films as well. I was seeing some of the instances of using video generation in full-fledged filmmaking. Like I was watching this Mahabharata from, I think it's telecasted in Geo, and it kind of like was subpar. Right now, like we could not capture the emotions, but nonetheless, it was an attempt to produce full-length videos with the help of generative AI. And we are seeing many, many advances in this field, and the world that is about to come is really, really exciting. So what we will learn about today is text generation and the intuition behind it, and maybe some math. How do we generate this text? So I'm really interested to dig deep into the large language models with you. So let's talk about text generation and how text is generated by ChatGPT. So if you have kind of like observed ChatGPT and any other large language model for that matter, it generates these words word by word, right? So if you type something on ChatGPT, let's say any question, then it generates the response word by word. It is not generating all the response at once. This is not some fancy animation that ChatGPT has done in their user interface. It's how exactly it is generating. So ChatGPT generates text by predicting the next word in the sequence. And this is what we saw in language modeling as well, where we were trying to predict what would be the next word in this sequence when I type I want to. And in language modeling, it was doing it with search and count methods. So if I see a table here, after I want to, there are many words that can complete this sentence, like I want to cook, and after that food will be the next word. I want to play, and after that games and music, depending on how many times people are searching I want to play games, comparable to how many times people are searching I want to play music. And then I want to watch movies or sports, again, depending on how many times people are searching movies and how many times people are searching sports. And finally, I want to work is being given the less priority because very few times people search for I want to work, right? So language modeling has been around there since 1980s, and it's been more than 40 years that we have been interested in computers generating natural language. And this method was very particularly popular at that point of time. We used to call that n-gram models, where we are predicting the next word purely based on what is the word that has occurred before. And we used to use the count and search methods to do that. What changed is we shifted to large language models, and large language models, ChatGPT uses something called large language model and not the language modeling that we used previously. That means that it doesn't use the n-gram methods to predict the next token. So large language model is basically a very large neural network, which we train on very large corpus of all the text that we can see in the English language. And then we train this very large neural network on that huge corpus, and the neural network somehow learns how to predict the next word that is about to come. We will see in detail what these large language models are, how we can make them, and also we will create our own large language model in this bootcamp. But let's take one step at a time. So let's say we take an example of what is the tallest building in the world, and we want to ask this question to ChatGPT, and we'll see how ChatGPT generates the answer to this question. So the first thing that ChatGPT does in order to answer a question like this, which is what is the tallest building in the world, is it chunks this whole sentence into smaller parts, which we call as tokens. Here in this case, if I talk about this sentence, what is the tallest building in the world? It chunks this sentence into 9 tokens and 42 characters overall. So if you go to this platform.openai.com/tokenizer, you will be able to see how all of the ChatGPT models are tokenizing the sentence. So we need to, computers don't understand sentence, right? They only understand numbers. So we need to break down sentences first into words, and then these words we need to kind of like represent as numbers so that computers can understand these numbers and find a relation between these numbers in order to kind of like generate words. So since we have started computing, we always deal with like zeros and ones, and we always try to represent characters as well as words with these zeros and ones. And uh, and the first step to do that is to tokenize it. That means that to chunk down whatever text that we have into smaller parts, which we call as tokens. So what happens is that ChatGPT, if I take it as a black box, that means that we don't know what happens inside. We take ChatGPT as a large language model. I'm using ChatGPT as an example because ChatGPT is the one which is more popular. I could have used Claude, Llama, and Gemini for the example as well. So whatever large language model that you are using, it's following the same kind of principles. So first thing is that we take the sentence and we chunk it down into tokens, which you can see from color coding here. What happens with these tokens is that all of these tokens, they go parallelly to the large language model. And the large language model kind of like has an idea of how these tokens are related to each other and how language actually works. So it generates the next token, which is the best fit or the best token after we complete our prompt. So if the prompt is what is the tallest building in the world, question mark, what is the next token that it should generate, right? So generally the answers, they start with that's why ChatGPT is trained on general talks. So that's why it will generate the. Otherwise, if I ask this question to a human, what is the tallest building in the world? Maybe he will answer it with Burj Khalifa, right? But we don't write language like that, and human beings don't talk in a way like that. So if a question is being asked, we kind of like try to complete that sentence with a answer. So the case here will be that it will generate the as the next token. That means that it is predicting that after question mark, the should be the best fit in this case. Then what happens is that it takes this the as the input, and all of this text along with the as the token goes into ChatGPT, and it generates the next token, which is the tallest, right? Token is nothing but a chunk of all the sentences. If we chunk the sentences into different parts, it can be a word, it can be phrases, it can be characters, it can be symbols. Here in this case, it's mostly words, and we have one symbol also here, which is a question mark, right? So once it takes in this input, the also as the input, it generates the next token, which is tallest. After taking in tallest as the input, it will generate the next token, which is building. After taking building in as the input, it will generate the next token, which is in. After taking in as the input, it will generate the next token, which is the. And after taking the, it will generate the next token, which is world. And then it will generate is. And then it will generate bur, because bur is more frequently used token. Therefore, it is generating bur. Otherwise, it would have generated burj as well. So it is taking in two tokens, BUR and J together. I'm just spitting them both together, but it will generate BUR, and then the J will be the next token. And after Burj, it will generate Khal as one token and IFA as another token, because Khalifa as a word is not that much common in English language. That's why Khal and IFA are being separated. So it will generate Khal and then IFA, and then it will combine them together to form Khalifa. So in response to what is the tallest building in the world, it will spit out this response that the tallest building in the world is Burj Khalifa. And then after generating all of this sentence, it will generate something called the end of sequence token, which is an indicator to ChatGPT that the sequence has ended. That means that the answer has ended, which is similar to what we see in English language as full stop. In other languages, the end of the sequence token can be something else. Like in Hindi, it is Purnaviram. In Chinese, there is no end of sequence token. In other languages, it can differ variously. So the idea is that the large language model or the generative AI, which uses these large language models, are just predicting the next token in the sequence, right? So just by predicting the next token in the sequence one by one, it is generating the whole sequence together. All right, so maybe I will just share my desktop and maybe we can give it a go as well. If we go to, let's say, ChatGPT, for example, GPT, and if I open ChatGPT, then if I ask this question, what is the tallest building in the world? Then you will see that it will generate it token by token, right? So it is kind of like not giving it faster, the tallest building in the world. And now it has also started giving the pictures. The tallest building in the world is the Burj Khalifa in Dubai, United Arab Emirates. And it is kind of like generating it word by word if you have observed the animation. So it's kind of like predicting only the next token. Right now, it's also predicting complex tokens like these emojis, and also right now it can search for the images. So we have gone a long way in these generative AI models, but the core remains the same, that it only predicts the next tokens. If you are catching up along the newest news headlines, then if you have heard the Yakun's uh, uh, Yakun's address in AI Summit, then Yakun was telling that the true intelligence will be when we move beyond these text models. That means that when we move into causality of systems, human beings don't are not intelligent just because we can predict the next word in a sentence, but we are also intelligent because we know the causality of the systems. That means that if we do something, what will be the consequences of that? We also understand that part of the world. But nonetheless, we have these models as the benchmarks of intelligence in the world right now, where we can only predict the next token in the sequence. So this also gives some kind of like reasoning capability to the large language models. This also gives some kind of intelligence that it is able to predict what comes next. But still, we are far behind true general intelligence, which is true artificial general intelligence, which will be when we move from these token or text-based systems to causal systems, where we also talk about what will happen when I generate something like this, or what will happen if I do a particular action. We will talk about causality. We will talk about a lot of things about general intelligence also, along with whatever we are dealing it with right now, which is the state-of-the-art intelligence system that we have, which is large language models. So if we say that it is predicting the next token in the sequence, how it is actually doing that, maybe we kind of like go into intuition of it. Maybe we also will start with the transformer architecture. How does it predict, and how can we create a large language model of our own? In the next sections to follow, we will code it from scratch. We will have a large language model of our own. But let's do a primer of it. How can we design our own large language model? So large language models are just two files. So if we design our large language models, we will only be having two files. One is a parameter file. If you talk about ChatGPT, then it's a 175 billion parameter file. It's around 800 gigabytes of data. And the other file is a run.c file, which is kind of like 500 lines of code. So we take all the data, all the text that is there on the internet, we kind of like compress them into these parameters, which are these weights of this very, very large neural network, right? So we have a very large neural network, which works like similar to how human brains work. So in humans, there are different neurons which are connected with each other. Similarly, in artificial intelligence, we have a neural network in which there are nodes and branches connected to each other. So we kind of like distill all the information that we have on the internet, all the text that we have, into these 175 billion parameter models, parameters, and which is roughly around 800 GBs of data. So trillions, the TBs of data, thousands of TBs of data of the world, whatever text that we have, we are compressing it into this 800 GB of parameters, which we run with a run.c file. So when we design our own large language models, we will design our parameter file, we'll design our run.c file, and we can see that just with 500 lines of code, we are able to do tasks as sophisticated as ChatGPT. So these large language models are just two files which we store on cloud. So ChatGPT stores it on clouds, it runs on GPUs, and then you can talk to this in natural language. The neural network looks like this. This is kind of like a diagrammatic representation of neural network. It's kind of like a software architecture where we take in nodes, and these are the weights that are connected from one node to other node. the parameters are weights and biases of this neural network. So if you see, there are 3 nodes connected to 8 nodes. So there are 24 parameters. That means that these weights of these 24 connections, and we add a bias term in order to stabilize this neural network. So if you see this small toy neural network that I'm taking into consideration right now, it has 122 parameters, right? So you can think of a very, very large neural network like ChatGPT, which has 175 billion parameters. So we are training a very, very large neural network in order to learn language, in order to learn these weights, which can learn language and the sense of language, and we can talk to this neural network in natural language, and it understands our language, it generates our language as well. So to make a large language model, we only need 4 things, and these are the 4 steps. We need lots and lots of data to train a large language model, which we call corpus. This corpus we get from scraping the web. So we kind of like use web scrapers. These are certain tools which go to each website, and they take in all the text that is there in the website, and we take that text in a file which we call as corpus, and we train our large language model on that corpus. Second thing that we need in order to train our large language model, and how ChatGPT was generated and how it was made, is the transform architecture. So it's kind of like a programming architecture which is needed or required to code ChatGPT. This transform architecture, it's architecture to train that huge neural network in order to learn language and generate new language. Then we need lots and lots of GPUs because we are processing everything in parallel, as I showed in the previous sections. That means that we are feeding all these sentences, we are chunking them into tokens, and we are feeding them into parallel. CPUs are not very good in handling parallel information. That's why we use GPUs, which are graphical processing units. And we need a lot of money in order to buy these GPUs. So ChatGPT was trained on 60,000 GPU clusters of them, and we trained them for 60 days, and it required $100 million in order to train ChatGPT alone. And finally, what we do is we fine-tune our model. That means that we fine-tune our model on the data that we want it to behave like. So ChatGPT was fine-tuned for general purpose. That means that it can talk to us in a general manner, like a human talks to other human. So fine-tuning is once we have that model, once we have these weights, once that neural network learns how to speak language, we want it to also use for particular use cases. And that's why we use fine-tuning, where we kind of like mold our large language models in order to behave it like we want them to behave like. The recipe of designing a large language model is fairly simple. You make a very, very large corpus. We train the language model, we fine-tune the model, and the model is ready to talk to us. So step 1 is building a corpus. So how can we build a corpus? We build a corpus by scraping the web. So we use these web crawlers that go to each of the websites. They go to Wikipedia, Quora, social media, GitHub, Pinterest, articles, and blogs. They take all of the data that is there, all of the text that is there in these websites, and kind of like scrape that text, extract that text from there, and it merges that text into a single file, which we call as corpus. The larger the corpus that we have, the better our model will be, because it will be seeing more words, it will be seeing more context between these words, and it will be better in understanding the language. Okay, so before I move ahead, I have some polls as well for you, so that I'm not the only person who is talking, and we also have some interaction. So before we move ahead, quickly tell me in the chat box if you have any questions so far, and what is the answer to this question. How does ChatGPT generate text? Is it A, it generates paragraph by paragraph, B, it predicts the next and the next word only in the sequence, C, it predicts the whole next sentence and displays it, or D, it generates the whole document at a single time? I'm also reading your questions that I am encountering. A lot of people are saying B. Thank you so much, Ashish, Tanishka, Yuraj, Prabhat, Ambika. Yuraj is saying C, that it predicts the whole next sequence. Shravani, Shashini, all of you are saying B. That means that you are listening to the lecture very, very focusedly. And also, you know something about the large language models prior as well. Thank you so much, all of you, those who have been answering. It's wonderful to see huge participation. Maybe we can keep the momentum on and interact more on the chat. So I will read some of your questions if there are any, apart from the answer that I am getting on the large language models that I am here seeing. If you have any question interesting, or if you want to know some more concept, maybe you can ask the question as well, apart from just answering the question that we have on the screen right now. Pranav has a question: how AI can help, and which all tech are used in drone development for defense and agriculture? Okay, Pranav, it's a very, very interesting question. And so drone development is where you are moving on to physical AI, which is the next big thing which is going to come in the world after generative AI and agentic AI. So the world moved from predictive AI to generative AI to agentic AI, and the next big thing is physical AI. So physical AI will be a combination of large language models which can understand certain instructions. It will be a combination of vision language models which can also learn from YouTube videos how to do certain tasks. So if you're interested in making a drone and developing it for defense and agriculture, maybe you can research about vision language models, which are kind of like language models which train itself on videos in order to perform certain tasks. All right. Some people are saying that it's not live on YouTube. I think in YouTube, the poll is not available. The poll is only available for Zoom users. All right. So thank you so much, Tanvi. Thank you so much, Saad. Thank you so much, Aruna. Aruna is asking how AI can help in stock market analysis. Aruna, it's already helping. I think if you have seen apps like Zerodha or maybe kind of like apps like Upstocks or maybe NGL1 or some of these, they are using AI in stock market analysis. Basically, AI is gulping a lot of data from stock market. It is kind of like making sense of the stock market data and trying to predict which of the stocks will soar. We kind of like won't cover the stock market analysis with large language models, but definitely you can also use large language models to predict stock market as well. Deepak is asking, this is the final question that I'm taking right now, then we will move ahead in the session. Deepak is saying that, is it possible that AI might become sentient ever in the future? How can we code emotion into AI? I believe that we will be able to generate artificial general intelligence. However, emotions and emotional intelligence is something which human beings are able to display. And we have been displaying emotions very recently. So in our evolution, if you see, of 10,000 years of evolution, only 5,000 years back, we have started to kind of like write language and express our emotions in form of language. Although emotions, like animals also, they kind of like depict these emotions. But as we are moving into tech, as we are taking in more and more data from the environment and the real world, maybe in the future we will be able to predict the next emotion. But until and unless we go to the causality of it, like large language models and the AI that we have right now is predictive AI, right? We can only predict what might happen next. If we move from predictive AI to causal AI, that means that we also know the consequences of what actions that we will do. Maybe we will be able to kind of like impart emotional intelligence into AI as well. When AI knows that, okay, if I say this to someone, this is what the outcome of that sentence will be. Right now, AI just says the best word that it might say. It doesn't think about the consequences of those words. So once we move into causality of the systems, I'm sure that in the future we will see more sentient type of behavior from the AI as well. Okay, so let's move forward. Thank you so much, those who have been asking questions in the chat, as well as those who have been responding with the question and the answer. All right, so we have cracked the first step. The first step being that we had to make a huge corpus. That means that we scrap all the data that is there on the internet and we kind of like extract. There are some things that we need to keep in check on the data that we extract from internet. That means that we need to filter that data for training, because from internet we also might get data like HTML tags. We need to filter that out. We only need to train our large language model on text. So a lot of pre-processing is also required before we start training the model. Step 2, training is relatively simple. Getting the data is kind of like difficult, because we have to filter, we have to pre-process, we have to remove the harmful content, we have to remove whatever content that we don't want the language model to predict, right? So if you ask ChatGPT how to make a bomb, maybe it will not answer you that question. Why? Because it has been this kind of data has been omitted from ChatGPT. But however, you can kind of like jailbreak ChatGPT in order to answer these questions as well. But we will talk about them in later sessions. How we can jailbreak ChatGPT, how we can jailbreak large language models to provide us answers which it is not trained to provide as well. But talking about training, which is the step 2. So in training, it's fairly easy. So we randomly cut the sentence from the training data. So we kind of like have all this data that we have with us. So let's say that we want the language model to predict that Taj Mahal is in Agra. So what we do is we randomly cut this data from any random place, and we ask the model to predict what can be the next word in this sequence, right? So we have a huge neural network. We put in the input, which is this input, and we ask it to predict the output, which should be Agra. Now, in predicting the output, what will happen is that first it will start with something gibberish, because it does not know anything about Taj Mahal or anything about Yamuna. So it starts with something very random, like it can produce something like Yaya, and that's not the right word, right? So we know that the right word is Agra. So we kind of like ask the neural network to adjust its weights and biases. We back propagate the error. So we calculate the probability of the words. The right word is Agra, but you have generated Yaya. So calculate the error that you have, and you back propagate that error in the neural network. You compare it with original sentence and adjust the model. So what happens is that so yeah, if we want to predict the Taj Mahal is in Agra, but somehow the model knows that Yamuna also flows through Delhi. So maybe initially what it will happen is that in training this large language model, these weights and biases, they will get adjusted such that it predicts Delhi as the right answer, right? So let's say that at the first instance, it produces Delhi as the right answer. It says that, okay, I know Yamuna is in Delhi, so maybe Delhi might also be the right answer according to the weights, what they have learned so far. So what will happen is that whatever error that we get between Delhi and Agra, we kind of like feed that again in the large language model. Again, these weights and biases, they kind of like adjust. The value of these weights and biases, they adjust till it predicts Agra with 99% accuracy. So we know that Agra is the right answer because we are training it on the corpus that we already have, right? So in this process, again and again and again and again, we keep doing that for all the text. So we randomly cut a sentence, we ask it to predict the next token, it predicts something which is wrong, we calculate the error, we backpropagate into neural networks, we again predict the next word, we randomly cut the whole corpus from different parts, and in this process, it learns how to relate certain words with certain words, right? So ChatGPT took 60 days to train on 60,000 GPUs to get this neural network of 175 billion parameter model. So we'll do it step by step when we will go into like designing our own large language model from scratch, from code, very intuitively. We will see all these steps happening. Until then, we can only have the assumptions of how the weights are changing in between. So one major thing that how is this prediction happening, right? So how are we training these large language models? So we said that we randomly will cut the sentence, but how will it help the language to understand the model to understand language is what we talk about next. So the text prediction or the way to train these large language models is through transformer architecture. So in 2017, if you also see the full form of GPT in ChatGPT, you will see that the full form of GPT is generative pre-trained transformer, right? So transformer is right there in GPT's full form itself. So it generative because it generates some new language, pre-trained because we have trained it previously on some data, and transformer because it's the architecture on which it is trained on. So what are transformers? If you talk about transformer architecture, it occurs first in in AI in 2017 by this paper, Attention is All You Need, which is by Ashish Vaswani sir, Nikki Parmar ma'am, Naum Shazir, Jacob Uskorit from Google research team. So what they did was they were trying to figure out how can computers understand language. And in the process, they came through this architecture called transformer architecture, which looks like this. Okay, now this kind of like looks like a scary figure, but I will explain it in very, very simple format so that all of you can know about this. So this transformer architecture is a programming architecture in which we code our computer to understand language. It has two parts. One is the encoder part and one is the decoder part. So the encoder part looks like this and the decoder part looks like this. The decoder part of this transformer architecture is what we will use for generating language. So translation happens when we have input in one language and we generate another language, right? So the researchers, they said that we don't need the whole architecture. We don't need the input in one language and we don't need it to generate in another language. We need the input in one language itself. So here we are kind of like using the input in one language from below in the decoder part as well. And then we follow the whole process. And finally, it generates the output in that language only. Okay. So if you see about this transformer architecture, then one thing that you can have a mental picture about is you can treat this transformer architecture as a 5-story building. So this is story 1, this is story 2, this is story 3, this is story 4, and this is story 5. Okay, so let's say that we have a 5-story building and we are entering this building from the lowest level. And the output from this building is a new word. So the words are entering this building from a very first or the ground floor, and they are getting out of this building from 5th floor. Okay. So the first floor of this transformer architecture or this coding is word embedding. Okay. So before word embedding, we already have our outputs or the inputs here as tokens. This we already have done previously, right? So all the sentence, if you want to predict something after this, so let's say that this was the input and we wanted this transformer architecture to generate the next word in this sequence. This is what a large language model does, right? So it only generates the next word in the sequence. So let's say that we have something like apples are a type of delicious, and we want to predict the next word in the sequence. So what we do is we already chunk them down into tokens, which we already have done with tokenization. Now we input all of these words in parallel to this transformer architecture. So the first floor of this transformer architecture is input or the word embedding. So computers don't understand words, right? Which we already have established. So they only understand numbers. Right. So how does computer understand language, right? So I have a quiz time for you. So we treat words as not just numbers, but word as vectors. Okay, so if I ask you this question, king minus man plus woman equal to what? What will be your answer in this block? Okay, so if you have answer, then you can give me in the chat and maybe we can discuss further from that answer. So if I ask you this question, king minus man plus woman, what would be the answer? Aditya has given me an answer, which is queen, which is the right answer, right? So, but how are we kind of like doing and subtraction and addition with words, right? So we say that we can't add words or we can't add or subtract words, or we can't make mathematical calculation in words because we can only make mathematical calculation in numbers, right? So if I say king minus man plus woman equal to what, all of you are saying the answer that it is queen. Some of you might also say the answer as king wo, which also makes sense because if I cut man from this and man from here, maybe I can also have answer like king wo. But generally human beings don't see relationships like that, right? So we see a relationship that, okay, king might be some position, man is man. If I subtract that king man from king, there is something which is position. And if I add position to a woman, that higher position to a woman, maybe that higher position woman will be called as queen, right? So we generalize, we kind of like relate words in that way. So the similar kind of concept is also used in in transform architecture. In the first layer, what we do is we convert word into vectors. So king, man, woman, and all the words that are there in English language, we convert them into vectors. By vectors, I mean that I convert them into numbers, but these numbers are not numbers alone. Then these numbers also have a direction. So if I also say some more examples of this is if I say India minus Delhi plus Paris, which is France, right? So if I subtract Delhi from India, maybe I am left with something called country. And if I add country to Paris, then maybe I can relate it with France, right? So if I have like something like India is a name of a country. If I subtract Delhi from India, which is kind of like capital of India, maybe I only left with some sense of country. If I add Paris to that country, if Paris points to that country, then France would be the answer. This is how we relate things, right? So if but how can we subtract words, and how can we subtract and add words is one of the fascinating concepts in natural language processing. So we treat word as vectors. That means that we take in these word vectors. Now I can only draw a two-dimensional picture. So maybe queen and king are in this quadrant, which is the first quadrant. Man and woman are in this quadrant, which is the fourth quadrant. And this vector is like, in reality, this vector is a hyperdimensional vector of many, many, many dimensions. General way of these dimension is 300, but I can only show a two-dimensional vector. So if I subtract man from king, so this will be a negative of man. And if I subtract that from king, if I project this vector here, maybe I will end up with some vector like this, which can be a position vector, right? Because if I subtract man from king, I end up with a higher position only, a sense of higher position. If I add woman to this sense of higher position, then I will end up somewhere here, which is queen. Maybe I have better diagrams for this. So if I subtract man from this, I will take negative of man. And if I add this negative of man to king, then I will have something, a vector like this, which can be a higher position vector, which only tells that this is a higher position because king minus man is nothing but a position, right? If I add woman to that higher position, I will get queen, right? So treating word as vectors, that means that they lie in this hyperdimensional plane, meaning these words which are closer to each other, they have a relationship with each other, is the core concept of converting word into embeddings. There are many ways that we had converted word into embeddings. One way of doing it is using one hot vector. That means that we are treating all the words separately. So we are treating all the words that are there in English language as if they have no relation with each other, right? So let's say we start with aardvark and we end up with Zulu, and we only give a 1 in a place where that word has occurred. So let's say that abacus I want to encode, I am putting 0 in all the places and only 1 is there in the place. But this one hot vector kind of like embedding does not give any relation between these words. So abacus is entirely different word, abac is entirely different word, Babylon is an entirely different word, and they have no relation in each other. So primitive way of denoting word as vectors was also one hot vector, where we encode each word as its position in this whole vocabulary of English language. One more way of denoting these vectors is by word count. How many times in one document my word has occurred. So this is also called as term frequency and inverse document frequency. So this is a sparse vector which is counting the number of times this word has occurred in all the documents that I have. So this also gives me some sense of understanding between words. In one document, there will be some kind of words together. We use that in bag of words where we treat words as these sparse vectors, where we make them in order of term frequency and inverse document frequency. All right, so next is one more type of maybe doing word embedding is by co-occurrence. How many times two words are occurring together in a sentence. So aardvark and aardvark might have occurred 176 times in my whole corpus. Aardvark and aardwolf may have occurred 16 times. Aardvark and Aaron may have occurred 234 times. This is also one of the type that we can convert these words into vectors, right? So aardvark is this vector of all these values, where all these values represent one dimension. So this vector is of the dimension of all the words that are there in the English language. And after we convert this word into vectors, we calculate the number of the distance between these two words. So we kind of like calculate the Euclidean distance, how far mango and apple are to each other. And we calculate this distance, and we vectors which have like similar meaning, they lie in the similar plane, and vectors which have no meaning at all, they lie in orthogonal to each other. So they lie in like different planes. We also can notice the similarity between these two vectors by calculating the cosine similarity, which is kind of like the dot product of vector A and vector B. If two vectors are in same dimension, let's say mango and apple, maybe they both will have some score of A dot B. If they are perpendicular to each other, like in here, their dot product is 0. Right, so mango and snowflake have no similarity with each other. That's why the similarity score is 0. If apple is there, then mango and apple, if they are in same dimension, then their similarity score will be something, and we will say that okay, these two words mean same in English language. So basically, by converting word as vectors, we are trying to impart dictionary meaning or the semantic meaning of the word as into words. So we are trying to find out which words lie closer to other word in any language, right? So mango, apple, banana, they will lie closer to each other in this vector space. Snowflake and maybe kind of like ice cream, they will lie together in this vector space closer. So the words which are closer to each other, they will be more similar, and they will have more understanding between each other. They will have more context between each other. Mango and fruits will have more context rather than mango and snowflake, right? So we kind of like try to learn that these words, which words are similar to what words, in order to make computers understand language. So the goal of large language models, and any language modeling for that matter, is to make computers understand language. Okay, so once we have a word as vectors, what we do is we also want to know the position of these words, how they are coming in this transformer architecture, or how they are coming in this neural network, right? So we are training a large neural network to learn about this language. We are training the neural network to learn language. So we need to know what position of these vectors are, or these tokens are. Why? Because we are feeding all of them in parallel, right? So app is being fed parallelly, less is being fed parallelly, R is being fed parallelly, and all these words are being fed parallelly to my transformer architecture. So I need to know the position of which word came when. So English language, or in any language, position matters a lot, right? So if I say dogs eat bones, and if I say bones eat dogs, so if I kind of like change the position of bones and dogs, although they are grammatically correct, but this doesn't make any sense, right? So dogs eat bones and bones eat dogs, although they are grammatically correct, this doesn't make any sense because bones can't eat dogs. So position of the words, they matter in any language. So at this second part of my building, I need to know which token came when. There are different methods of positional encoding, and we need to know the position, that app is the first token, less is the second token, R is the third token, A is the fourth token, type is the fifth token, off is the sixth token, and delicious is the seventh token, right? So we need to learn this. So a very, very interesting way of doing this is using sinusoidal waves, which we will tackle when we kind of like start designing our own large language model or our own ChatGPT kind of thing. Okay. Now the next and the most important part of this architecture. So we are coding. So we are coding everywhere. So we are coding here. We are coding words into vectors. That means that we are trying to find words which are similar to each other in this in this vector dimension, right? So words which are together in this vector dimension, they will be similar to each other. But but just the similarity of these words don't make a computer understand language, right? So we also need to know the position of the words, how they occur. And also English language and any language for that matter don't work on just the similarity or the denotation of that model, of that word. So in English language, the dictionary meaning and the contextual meaning of a word in a sentence are very, very different. Okay. And we need, in order to generate language, in order to generate or understand language, we also need to know how the word is being used in a sentence, right? So I will explain this with a very, very simple example. So let's take this as an example, right? So the sentence says the elephant could not fit in the car because it was too big. Okay, so if I want to know what it represents in this, okay, so it in English language, it can mean animal, right? Or it can mean a object. So it can mean an animal, it can mean an object. So what does it represent here? Should it represent elephant or should it represent car, right? So the dictionary meaning of it will not be able to teach a computer what it represents in this sentence. So that's why we need attention mechanism, which is the core of this transformer architecture. So we need our neural network to also learn that it represents elephant or car in a picture, in a sentence, right? So if I ask you this question, if I want to know the meaning of it in this sentence, what will be the word that it should point to, right? So should it mean elephant or should it mean car in this sentence? So just tell me in the chat box what is the answer to this question. What should it represent in this scenario? So Zeba is saying that elephant should be the answer. Akansha is also saying A should be the answer. Afshan Khan is saying elephant. Yes. Harichandran is also saying elephant. And Priya is also saying elephant. Yes. So elephant is the answer. Why? Because if I look at these three words, okay, I only need to pay attention to elephant, car, and big in this sentence in order to know what is the meaning of it in this sentence, right? So I'm teaching computer language and I'm saying I want in this mechanism, I want the computer to look at certain words in order to understand what is the meaning of it in this sentence. If I change this sentence and if I make this sentence as this, the elephant could not fit in the car because it was too small. Now, what will the it represent in this? Should it mean elephant or should it mean car? Right? So now the context will change, right? So if I talk about the elephant could not fit in the car because it was too small, now it will start pointing to car. Why? Because I am now paying attention to small here, right? So if I pay attention to elephant, car, and small, then I know that it should now be small, right? The meaning of it should be small. So the meaning of it should be small because elephant are not, sorry, the meaning of it should be car because if I pay attention to small, elephant is not small, car is smaller than elephant, right? So I am able to find out the meaning of it as car because I'm now paying attention to small in this sentence, right? So this mechanism or this discovery of paying attention to certain words in a sentence so that it mean paying attention to certain words in the sentence so that we can know the context of that word is called attention mechanism, right? So what happens in transform architecture and how does it do attention? So each word, so previously we converted this word vector into different vectors, like this word into vectors. Now what we do in attention mechanism is we convert these tokens or these word embeddings into query, key, and value vector. Okay, so we convert them into query, key, and value vector. So think of it like query is something that we are searching in some other word. So let's say some attribute that we are searching. Okay, so if we take this example of apples are a type of delicious, and if we want to predict what should be the next word in this sentence, there can be three possibilities, right? Apples can be fruits, and apples can be snacks, and apples can also be laptops, right? So I have fruit as one possibility, snacks as one possibility, laptops as one possibility. So what should be the best word that should fit here? Or what should be the best word that I predict? So in order to predict the best word in this, I need to look at the words which I should pay attention to, okay? So what happens is that the query vector of each of the words here is multiplied with the key vector of all the words to find a score, which we call as value. Okay, so what if I talk about this very intuitively, then apples as a word should have key or a representation of maybe something like plural, because it's a plural word, right? So the key of apple would have something like plurals or a group of objects as a meaning, because apples as a word represent plurality. Then R as a word, it represents again plural, a form of is. A as a word, it represents singular. Type as a word represents the class or classification. Of as a word represents preposition, and delicious as a word, it represents the attribute, right? So delicious will have different type of words in its representation. Like delicious can be sweet, delicious can be apples, delicious can be mangoes, delicious can be bananas, delicious can be other type of recipes as well. So in my delicious as a word, there is already a lot of words hidden, or in the key of delicious, I also might find apples somewhere, right? Because apples are also delicious. So the score of apples and delicious, if I want to search apples in the key of delicious, then the score is more. The chances of finding apples in the delicious category is higher. So that's why the score of this is higher, right? So I need to pay attention to apples and delicious in order to predict the next token. So if I see apples and delicious, then maybe we will be able to predict fruit, because apples are delicious fruit. And laptops cannot be delicious. We don't eat delicious, so laptops are not the right word. Apples are a type of delicious snacks is also not the right appropriate word in this, right? So in order to find which words do we need to pay attention to, the researchers, they have multiplied the query vector with the key vector of all the vectors that are there in order to find the value of that vector. Once we have the values of these vector, then we multiply them with the value vector, and we have our we have something which also has the contextual meaning of these words. So after this layer, the word vectors, they also have the contextual meaning of the inputs along with them. So we multiply the query vector of all the words. It attends to all the words that are there in the input, and it kinds of like selects which words I need to pay attention to in order to predict the next word. After we add in the values of these contextual embeddings, we send the input to a feed-forward network that just imparts non-linearity. So neural networks, if we talk about, the non-linearity in neural networks is very much required in order to make them more stable and robust. So we use a non-linear layer, which is a rectilinear function in this case. A lot of newer models, they use variation of ReLU like SWIGLU and GEGLU also, which are variations of rectilinear function. So rectilinear function looks like this. It has a 0 value for whatever comes, whatever negative value is there, and it is x for y equal to x. So the rectilinear function is a we use this in a feed-forward network as an activation function in these nodes. So whatever values are here, they are kind of like more robust when they reach the linear layer. So finally, we reach here with the word embeddings. Now the words, they also know that what it represents. They also know in which context they are being talked about. So once we reach the linear transformation, we try to map the next probable output with all the words that are there in the English language. And then we give a score to each word, right? So in the linear layer, what we do is we transform, we we do a mapping of the next word to all the words that are there in the English language, and we give a score to the words which are kind of like the next probable word in this sequence, right? So fruit is the next probable word because apples are a type of delicious fruits, because if we pay attention to delicious and apples and type, then the next word that is there in the sequence is fruit. So we are learning these parameters in order to predict this, right? So once we predict fruit in the linear layer, we have higher score to fruit. We normalize it. Basically, we kind of like try to try to normalize this from 0 to 1 so that we can convert these scores into probability. So here, if you see that we have converted all the scores into probability, and the fruit has the highest probability. So the word that is in the sequence next to apples are a type of delicious is fruit. So fruit is being predicted with the highest probability here, right? Snacks also can be one answer with 8% of probability, and laptops can also be one answer with 1%. But because we are paying attention to delicious and apples, the percentage of this is very, very less, right? So fruit will be predicted with the highest accuracy. All right. So let's talk about self-attention in a little bit of more intuitive details. Wait, I will just skip these slides. So to start from here. So basically what we are trying to build is we are trying to build a representation of the word delicious, and we will see that what kind of other words that it should look in my sentence in order to make the maximum sense of this word. Okay, so I'm skipping the math here. So I'm starting with very less intuition of how it might look like. So let's say that we start with apples are fruits as our example. So in the lowest layer, we try to convert them into word embeddings, right? So these word embeddings are nothing but these are weights of this neural network. So let's say that 1.87 and minus 1.45. And minus 0.78 and 2.21 for the end of sequence. So all these weights are connected to this neural network, right? So after I put in input any word, like we have them as one hot encoding. So apples are 100, apples are fruits is represented by 1000. After the first layer, which is word embedding, we are converting them into word vectors, right? So we are having these two representation or two-dimensional representation of fruits as a vector, right? So after we convert them into vectors, so let's say that so 1000 was apples was my input, and after word embedding, which is the first layer, I get a vector like this. So in reality, this will be a more than two-dimensional vector. It's around 300 dimensional vector. That means that we try to learn 300 values of this of apples. So we try to represent apples by 300 values, and so that if I multiply or do a dot product of them with the values of fruits, which are kind of like again 300 values, there should be some similarity between apples and fruits, right? So in the first layer, which is the input embedding here, I am converting these words into numbers. And these numbers are not sparse. That means that they don't have a value from 0 to 1, 0 and 1. They are continuous values like 1.87, 0.09, and up to the 300 dimensions that we have, right? In the next layer, we try to learn the position. So after we convert word into word vectors, here I'm converting it into 4 different vectors. We try to learn position of these words by using some methods. So one of the method is to take in these sinusoidal functions to learn the position of the words. So if I want to know the position of the word, if I want to learn the position, I initialize random sinusoidal waves like these, which are in dimension, which can be in dimension I. So I'm learning sine I up to 10,000 to square 1 by d. So all these sinusoidal waves will have different kind of wavelengths. And if I kind of like sample them at time. So if I sample them at first time, I may have some values which I get from here. If I sample them on second time, I may have some values which are here. If I sample them on third time, I may have some values which are here, and fourth time I may have some values which are here. So these values will tell where my words are in my position, right? So each of these values will be different. So we learn these values from 0 to 1. So we are learning for apples. I have these as word embeddings, and these are the position values that I have learned, right? So we are learning the position of apples also. We are learning the position of R, and we are learning the position of fruits also. So these positions are coming from these waves which are randomly initializing. And I'm saying that at time t1, when apple was there, then this was the value of this function. When R was there, then this was the value of this function. Then when fruits was there, then this was the value. And when end of sequence was there, then this was the value. So we are learning these values also. So adding the position also to my word embedding. So once I add the position to my word embeddings, I will have my word embeddings change from a one hot vector like this, which had apples as only one in one place, to something which is a continuous representation of values. So I changed this values which are um, in word embeddings. I converted them into word vectors first, and then I added a position encoding to these vectors as well. Now at this point, I also have position learned of apples or fruits in my sequence, right? So once I learn the positions at this point, so I'm converting words into numbers, right? So I'm converting them into random numbers here, which I'm learning from this neural network. So this neural network is learning these random numbers in order to make sense of these words. So after this positional encoding, I have words and position encoded values, which then go to the third layer, which is the attention layer. So, right. So what happens in attention layer is, I already have talked about this. So what happens in the attention layer is we again train a neural network to learn the values of query or Q. And we also learn the values of K. That means that if I kind of like search this word in context of this word, then how much is the chances that I will find the context, right? How much this word and this word are communicating with each other. So we are converting them into query and key vector. So we are learning some more values which we add to the word embeddings and positional encoding in order to convert these words into query vector and key vector. So in the next layer, what we do is we multiply the query and key vector to get some value, like 11.7 and minus 2.6 in this case. So if apples and apples are multiplied together, then there is a value of 11.7. And if apples and fruits are multiplied, then the value is minus 2.6. Then we compare these values and do a softmax, and we find out that, okay, we tend to pay more attention to apples. Apple should pay more attention to apples in order to make a sense of this sentence. Okay, so this is very small corpus. In a large corpus, it will these values will change. So finally, we also have a value vector V, which we multiply with this these two values in order to find the final vector or the representation of the words as the attention embeddings. So after we do all of this, after this layer, wait, in the transform architecture, after this layer, we represent word as not just words, not just numbers, but these numbers have first dictionary meaning here at this stage. At this stage, these numbers have positional meaning. That means that which word came first. At this word, these words have now contextual meaning. That means that how and what it should pay attention to in order to predict the next word. So after this layer, we have now converted my words into very meaningful vectors, which now not just have the word meanings, but also have the position and contextual meanings in this. So we start somewhere from Apple being 1 0 0 0 and only a position, only a kind of like one hot vector. So from this we could not learn anything, but from values of Apple as 2.5 and minus 2.1, which now also which has information that how word can be represented in this space and which word it will be closer to, plus which word it should pay attention to in order to predict the next word is what is encoded in these values. Okay. And finally, after the linear layer, in the linear layer, we kind of like map these words to all the possible words that are there in English language, and then we do a softmax so that we predict the next word which has the highest probability. The final thing that we will do when we design our own large language models is to fine tune our models. Okay. So step 3 is fine tuning. So fine tuning is when a large language model is trained on a large corpus, it is fine tuned according to our needs. So ChatGPT is fine tuned for general purposes. That means that it only gives general answers. Fine tuning means once we have trained this whole transform architecture to know about language, we don't want it to generate something which is very robotic, right? So we want it to fine tune on how humans speak or how we should want it to answer our question. So we fine tuned it on human feedback. So ChatGPT has been fine tuned on more than 30,000 by more than 30,000 humans, which have again and again taught ChatGPT that this is the way that you should talk, right? So fine tuning can also be done by human in the loop. You can also fine tune with dataset fine tuning. That means that you get you take your own specific data set. So let's say that you want to design a chatbot for hospitals. So you will add on in whatever terms that you use in hospitals, and then you fine tune your model with this hospital data. And then you can also do it with transfer learning. That means that you train it on one task and then you continue to training it on new task. Few shot learning, that means that in prompting, when we talk about prompt engineering, then in the prompting you give some examples in order to train the model to behave in a certain way, right? So if you train the model to just generate one word, so we are giving many different kind of like examples in order to generate just one word. So it will start learning that the user only needs one word sentence from me as an answer, right? So we will see how we can do this. Prompt engineering is when we craft effective prompts in order to guide the model in generating the desired output. So you must have been seen fine tuning in live as well. When ChatGPT or any large language model, it gives you different kinds of like responses, and it asks you to get or take in the right response, right? So here in this case, if you do a thumbs down, then it's a bad response. If you do a thumbs up, it's a good response. And this also trains the language model in order to generate what a human likes. Fine tuning is also done by giving a human response to a ChatGPT response. So let's say that once ChatGPT understands how to write language, if you ask a question like what is repo rate, it might answer it in a very robotic way. But you need a more human response. So you take in a human in loop, a human kind of like trains that model again by a more human-like language, which is written by here. And then it learns to talk like humans. So if you see, if you ask them question to ChatGPT, you will see that it almost always answers with great question, or maybe yeah, that's an interesting idea. So these kind of things have been purposely put in ChatGPT, and they are put in the last stage of designing a language model, which is fine tuning that model with our own data. All right, so this is a quick primer on how our language models work. So we started with how ChatGPT generates text, and we saw that we only need 4 things to generate a large language model. And we also kind of like got into depth of some math behind it. Although I skipped most of the maths because I know maths is one thing that troubles a lot of people. So I kind of like want to keep it very light and not really math heavy. But in order to kind of like make our own large language models, and if you really want to do make a large language model like ChatGPT, and if you want to train them according to your own needs, then this much of intuition or math you will require. All right, so we started with transformer architecture as the base of it. There are different other architectures that we can also use in order to train machines to learn language, like Mamba architecture as well. But those are beyond the scope of what we have achieved so far in language models, and everyone has used transformers only. So I'm going back to our large language models. So they are only requiring 4 steps. So we need uh, a lot of data which we can scrape from internet. We need transformer architecture. Basically, we are converting words into vectors and then adding position and then adding context and then mapping up with possible words in the English language or any language for that matter, and kind of like making them sum up to 1 and picking the word which has the highest probability, and that will become my output. And I do it again and again and again and again for my text, so that my model parameters, they adjust so that it learns these nuances of language, how language is formed, what words relate to what word, and all. And then we pre-train it on large GPUs, and then finally we kind of like fine tune it. We will design all of this in code from scratch in the sessions to come. Maybe we will also talk about agentic AI. Maybe we will also design AI agents that can work for us. Maybe we will use some of the pre-trained models from the internet and fine tune it to our own advantages as well. That's all for today's class. I hope that it was not too much overwhelming. I am open for the questions right now. If you have any questions or any suggestions and anything else, any top of the mind thoughts, you can share it on the chat box. And for the next 15 minutes, we can have a talk and then we call it a day. Thank you so much, those who have been participating in the chat box, answering questions and also asking questions. I'm happy to answer the questions for the next 10 to 15 minutes if you have any questions like these. So Neha is asking a question: can AI like ChatGPT replace teachers in the future? Why or why not? AI already, there are many apps that have been working in this domain. So teaching requires kind of like it kind of like is a learning agent which requires kind of like critique and so how do teachers behave is that they don't give you the answers directly, and language models they try to tend to give answers directly. So maybe if we can fine tune them to ask a question, understand where we are coming from, and then give an answer, maybe they will be able to replace the teachers in the future as well. And with agentic AI, definitely in the near future, we are going to see the replacement of teachers as well. Although it has, like I prefer to learn from ChatGPT rather than learning it from books. So it's a huge shift in the world that we are seeing right now. If you ask ChatGPT to explain something which is really difficult into a very simple manner, then yeah, probably it will also replace teachers in the future. Varsha is saying, yes, this is live in the YouTube channel. You can see it from that stream as well. Can we get the slide of it? Yes, we will get the whole PPT from our end. So CSR Box team will share that with you. Harshita is saying, can AI replace the jobs? It's already doing that, Harshita, and yeah, the estimate is that in December 2026, maybe we will not have software engineering jobs per se, and maybe by mid 2027, software engineers will be replaced by people who can create code just by envisioning or maybe by commanding AI to generate the code for them. So we used to always train computers and we needed specific people to train computers. Now AI can train computers for us, and that's a huge shift in the job market. And there are many different jobs that AI is going to take, but it's also creating new jobs as well. Like people like you who are interested in designing an AI system or developing an AI system, designing your own large language model, making computer understand language or some other thing, let's say a video or an image. If you can do that, then there are huge possibilities in the job market as well. So that's why this course where we are going beyond just using AI to actually creating AI. How can we kind of like create AI from scratch? This will help you to be stay ahead in the job market than the people who are just consuming AI for their use case. Arvind is saying, how do you ensure the data set provided to the model are correct? It's very subjective. So we need to kind of like do a lot of pre-processing. There are many guidelines and norms that are there in order to take that as a corpus. You don't want harmful, you don't want uh, text which is kind of like creating tension and all to be generated by the language model. So you don't want it to train with this. One more thing that we need to be very careful about is how do we want our model to behave? So Arvind, if I answer your question, if you want something like Claude Code, which is very good in coding, maybe you will need your data set to have more parts towards coding. Like 60% of your data is coding data and the rest of it is language. Um, Language models which are very good in logic, they also tend to be trained on more mathematics and coding data rather than the general data. So it's a huge process where we pre-process the text that we are taking from the internet. We are kind of like filtering it and then only adding it to large language model to train. uh, Jiffy Francis is saying that how to avoid biases in the data corpus. So one thing is to avoid biases is that you take an unbiased data altogether. But then again, what will happen is that internet is already biased. So how much biasness can you remove? So you can fine tune it with a smaller data set where the data set is kind of like unbiased, and then you are removing the bias from the system like that. Uh, Prachi is asking, when we convert long documents to vector database embeddings, we usually chunk them. How do we balance the loss of global context due to chunking with the improved search precision of smaller chunks, and what are the best techniques to preserve context? So Prachi, the kind of like we want to move into a world where we don't need to chunk these data, right? So the ideal case scenario when we move into artificial general intelligence is that when we do not have tokenization at all, like human beings, as intelligence beings that we are, we don't chunk language and then process it, right? So we process the idea of the whole sentence. Right now we are kind of like chunking, and there can always be some disadvantages of chunking, maybe kind of like a lost context because we are very far ahead in our contextual window, and maybe we forget the previous context and we are not preserving that context. Some models, they use kind of like memory to preserve the context as well, but again with moving into that the vector embedding dimension, we always will have some shortcomings. So maybe we need to move to a more advanced models like the state models, which I think Mamba tries to solve. Like if I am in state one, so let's say that I have an input in some state, what are the actions that I should take from this state to other state, and what would be my other state look like? So human beings, they kind of like talk in this way. So if I'm talking to you right now, I'm not chunking it into different words. And also if you are hearing it, you are not chunking it and understanding, right? So you are kind of like understanding the gist of it, and you are also kind of like mapping it to your future or maybe to your past or to your learning, which is not evident in language models till now. So once we move to that kind of systems, once we have these state transformation systems, maybe we will be able to design something which doesn't need tokenization at all. And that would be the ideal case when we move ahead from the text models to more causal language models where intelligence will not just be predicting the next token. It would be something like saying the next idea and also understanding the consequences of what I'm going to say next. Deepthi has asked a question is, sir, is there any chances of reduced scope of AI someday? Yeah, I think a lot of people are talking about the AI bubble, and this bubble will burst once we are very close to a technology like AGI. But in the next 4 to 5 years, I don't think that we are going to have less scope of AI. There will be always be much larger scope. Harshita is asking how to get jobs in AI and what skills are required. If you want to get jobs in AI, first of all, you need to kind of like make your goal very clear. What kind of jobs are you looking forward to in AI? Are you kind of looking forward to jobs like creating artificial intelligence, or are you looking forward to jobs like how can I best leverage AI to do some task, right? So if you have some skill already, so let's say that you are very, very good in painting. If you leverage AI for painting, uh, uh, so um, so I was listening to this very interesting thing, and I was reading it somewhere that okay, a painter doesn't sell its painting because it paints well, right? It sells its painting because the painter is famous. A painter who paints anything can sell its painting just by becoming famous or creating value for itself or for its paintings. So if you are someone who is into creative domain, maybe you can leverage AI to create something which is valuable that nobody is doing. Maybe AI is doing the thing, but the value is still there of your work, and people are paying you because of the value of your work and not just because AI can do it. Uh, so maybe that kind of area that you can also explore. If you are looking jobs in AI, then one interesting job can also be into how to find vulnerabilities in AI. How can I crack AI? How can I make them behave in a certain way which they are not programmed to, and then sell that information to all the companies that okay, I found this loophole in your AI system, and they will pay you happily for that. So there are many domains. You need to specify which domain that you want to go. And then there is agentic AI where you use pre-trained models to do some task for yourself. We will explore agentic AI. We will make our own AI agents in this bootcamp. So all of these things we will explore. But you need to be very clear which direction that you need to go into AI. And those are the skills that you will require in order to make a mark in that field. So if you want to design AI, maybe the skills that you require is coding and in math. If you want to kind of like use AI, maybe you need to be better at language and prompting. If you want to kind of like use AI for creativity purpose, maybe you need to develop your creativity and prompting skills in order to prompt the AI to leverage that creativity. And if you want to go to agentic way, maybe you need software development as the core skill. Uh, okay. Question Anugya Dubey is data scientist job safe after AI? It depends on what the data scientist is doing, right? So data analysis is going to be not in the market from the next year, right? So because AI can significantly do data analysis better than any human with any tool will do. So if you are learning something like Power BI or maybe something like Tableau and all, although they are like powerful tools in order to understand data, but AI can just do it very, very fast and very, very easily than all any human can do. So maybe if you are working in kind of like data pre-processing, maybe you can understand data better, what kind of data to feed to the AI to train. That kind of job is safe after AI. But if you are working in something like understanding the data, I think AI can understand it better than any human. Weber has a very interesting question. So he's asking how advanced is generative AI in helping robots move beyond repetitive labor into creative adaptive tasks? Should robots be allowed to learn if it reduces opportunities for human workers? If robots generate wealth, who owns it and how should it be shared or taxed? Yeah, that's a very, very interesting question. So GenAI, particularly vision language models, they are being used in order to train robots to learn from human videos and not learn from repetitions of the same task. Um, yeah, they're fairly advanced, and Nvidia and other companies are particularly working in creating more better GPUs in order to process these vision language models, because they are also kind of like very compute heavy. Um, I think the better path for humanity is to create robots which can work alongside humans and not as a replacement for human workers. And I think it will provide, if we can kind of like solve toughest challenges in the world through robotics, like let's say food security for that example. Everyone should have enough food. Pollution for that example, nobody should be kind of like, the earth should be clean of pollution. Robots which can go into dirty spaces where humans are still going. Like I was seeing a video where in India, kind of like people still go into potholes and clean them. Maybe we can design a robot that can do it for us. So tasks which human should not do, there are certain tasks which human does because of not because it wants to do it, but because of maybe um, uh, some kind of like um, majburi would be the right word in Hindi. Then I think designing robots for those tasks should be the core of robotics. And if they generate wealth, then of course the people, those who own those robots, they will be the ones who will be sharing it. Uh, Taxing, I think the companies who own those robots will be taxing. So maybe stricter laws will be made in the future, and we can't know what exactly will happen in future and what will be the new robotic laws. But maybe I'm very optimistic because I've been watching Star Wars all of my life, and I've been seeing droids and robots always existing along with these species in Star Wars. And I think that if we can create a kind of like that utopian future, and not the ones where they kind of like destroy humanity, maybe that would be the better future for humans rather than talking about robots taking our jobs and all. Prach is saying, even if we use linear time model like Mamba to handle infinite context, aren't we still fundamentally limited by compression loss in the hidden state? Yeah, of course we will be. So it's kind of like a matter of scale. Specifically, how does a fixed size state matter vector avoid the lost in the middle phenomena when retrieving specific facts from a million token sequence compared to a higher granularity precision of a well-chunked vector database? It's kind of like a very complex question, and scientists and researchers are still finding what can be the solution to the compression loss. Maybe we need better architecture, or maybe we need better hardware. Maybe we need to move into quantum space and not work with zeros and ones. And maybe we need more robust systems that can process these millions of tokens together. Uh, yeah, so that tech needs to be figured out yet, and maybe I'm not the right person to even comment on that. We can only speculate what can happen, but yeah, there are many people who are working in these dimensions. Maybe proper research would lead me to answer what is happening in the world. Right now, I can only guess that if we have a better hardware to compute these million tokens, maybe moving into quantum bits and quantum computing, we will be able to kind of like solve this compression problem. Malaysh Chenappa is saying, which agentic AI software we will use? Maybe we'll start with NA10, or maybe we'll start with something very easy to learn like Relay or Zapier, and then we will move on to LangGraphs. So we want to go into like depth of how to create our own agentic AI. LangGraphs would be the perfect way of designing them. So all these agentic AI softwares, they use LangGraphs to design themselves. LangGraph gives us more flexibility, it gives us more memory, it gives us more robustness. So yeah, we'll move on with LangGraphs in our bootcamp. Venkatesh is saying, is fine-tuning by human is necessary or it can be done by automatic in loop? Yes, we can also do fine-tuning by automating it. It's also called distilling. So a large language model is used to distill its learning to a small language model, and we can fine-tune a small language model also up to a certain accuracy with a large language model, kind of like fine-tuning it. So it can be done automatic also in loop, not particularly by humans. Uh, there is one more question. Is this Gen AI important for the one who want to become AI powered data engineer? Yeah, basically, we also want to know what is the tech that is recent. So large language models, particularly in data engineering and understanding data, they have been really, really powerful. So there is not only one use of generative AI. That means that it cannot just generate text, but it can relate between data really, really well. If it can relate between two words and it can tell that which word relates to what, then it can find many, many different patterns from unstructured and structured data as well. So yeah, underlying now world is moving towards more LLM based systems rather than more machine learning, which was in the past, because of the compute that we have been able to kind of like generate. We will very soon see a very small PC running a large language model, a 105 billion parameter model in itself, rather than running it on cloud. So, um, yeah, maybe with scale, the conventional methods, they kind of like tend to fade away. But yeah, it's also important to understand the basics of the conventional methods as well. Sakshi is saying, what will we do as software engineer, because everything is built by AI? You will use your creativity to prompt AI to build better solutions, right? AI cannot think of solving a problem. It can only solve a problem, right? So your idea is to find the problem and then ask the AI to make the AI to make a software that can solve that problem. So as software engineers, we'll be more than like understanding the problem, finding out the problem, asking the AI to solve that problem. So maybe you can take an analogy of how um, Tony Stark does that in Iron Man, right? So he's identifying a problem that, okay, maybe I need to invent a new metal in order to kind of like make this uh, a small power generator. Then it is asking AI to kind of like do the calculations in order to make this new metal. So that would be the role of software engineers. Maybe we will be more solving kind of like um, identifying the problem, solving these problems, uh, asking AI to do it, and maybe also keeping AI in check, right? So AI doesn't always particularly write code, which is better. So we need to also look for what are the things in the code that we need to change in order to develop better solutions. All right, thank you so much for all of your amazing questions, and maybe I was able to answer a lot. Maybe I will take the final one from Dhruv, which I have got. He says, in my software developer internship and my study, my degree is AI and data science, and I want to grow in AI field. Suggest me a, if I stay in this. I am not able to understand the question, but I'm thinking that the question says that what are the ways that you can stay ahead in this. Maybe the best transition right now, if I kind of like give advice, is look for advances that will happen in next 5 years, and in the next 5 years, the advances that will happen is AI will move from the digital world to physical world. So maybe thinking and learning about physical AI, and moving from traditional AI to physical AI would be one transition that you can make. Maybe you can start figuring out how can you make more physical AI systems rather than the digital ones which you already have. And then again, one more field could be how can you improve the digital systems that are already there? How can we make them more efficient? How can you make them run on very less hardware, like DeepSeek did with very less architecture, very less hardware? How can you make efficient algorithms? How can you make AI learn causality, and there are many exciting fields that are there. So thinking of new problems to solve is, I think, what will help you grow in this field. All right. Thank you so much for amazing questions. You can still connect to me on LinkedIn. My LinkedIn is Amit Tiwari. You can find me as Amit Tiwari space Edson AI. You can ask me questions there about robotics, about AI, about physical AI, about what we are doing, about agents and agentic AI. I would be happy to answer all of your questions there. We are towards closing of today's sessions, and I know that I'm super excited and super honored to have got these questions from you and answering these questions. But we can only take as the time permits. You can always connect to me on LinkedIn. So maybe I can help you with my LinkedIn ID, LinkedIn profile, which is a QR code to my LinkedIn profile. Maybe I have it in some of the PPTs. Uh, I'll just get one. Uh, Maybe I will have it in this one. Yes. So you can scan this QR code and maybe you will be able to connect with me on LinkedIn. My LinkedIn is Amit Tiwari AI, so you will find a similar kind of human which looks like this there. Thank you so much for your valuable time and joining on time. Maybe I will hand it over to the CSR Box team for attendance and all. You can freely connect to me on LinkedIn. Maybe we can discuss more ideas if you have ideas and you are stuck in uh, in making them execute. Maybe I can help you there in the process. Okay, so CSR Box team will share in the QR code of the attendance for today. I
All
hand
right.
it over to Anil and Prithviraj. Yes.
All right. Thank you so much, Amit, for such a wonderful session. I think there were a lot of questions stood by the students, and you answered. And I think all of you have enjoyed the session. So, students, you were asking some doubts regarding the certificate download, how to download the certificates, and also regarding the domain ID. So, we'll answer some of your questions right now. So, those who are not able to download or see your certificate, please follow the following steps actually. Right. So once you log into the platform, using the registration link, and if you have completed the introduction to large language model, then when you click on the first page under section 1, when you click on introduction to large language model, you will see there is one completed activity. So when you complete this activity, you click on completed activity, click on notify me, then just submit it. Okay. Nothing else. You just need to click on completed activity, completed this activity, notify me, then submit. After completing the session, okay, once you complete the session, then only you have to do this process. And after that, you will see again, come to the main page. On the right side of you will see 3 dots over here. Okay, on the same page, when you click on the introduction to large language model, on the first page on the right side of you will see a completion certificate. If you are logging, this is a screenshot of the mobile. So if you're using mobile phone, but if you're using a laptop, on just on the front page itself, you will see one tab called actions. Okay, there is a tab called action. So when you click on tab action, you will see the view completion certificate like this. View completion certificate, then you see like this. Okay. Right. So I hope all of you understood. Again, I will repeat it once again. All of you, please come to your first page. Log into the your GLE part assignment, self learning week assignment. Then go to section 1. Click on introduction to large language model. Then go to the right top side. You can see 3 buttons over here. Click on that 3 buttons. You will see view completion certificate. Once you click on the view completion certificate, you will be able to see your certificate. Right. If you're using laptop, then same process, but you will see one tab called
Anil, I'm
I'm
not
just
able to see your screen if you are sharing the screen. So maybe there is some tech glitch.
okay, I will share once again. Thanks for informing me.
No worries. Yeah.
Can you see it now?
Yes, now I can see. Thank you so much.
Right. So dear students, after logging into the IBM Skillsbuild platform, when you go to the respective GLE, the GLE link we have given. So click on the section 1. Click on section 1, then select your introduction to large language model. When you click on here itself on the right side, you will see 3 dots over here. So when you click on the 3 dots, you will get another screen. Then you can see the view completion certificate. Now you will be able to take the screenshot of the certificate. Right. So once you complete the activity, it may not be immediately visible there. It may take some time. It may take up to 24 hours to, reflect your certificate there. So I request once you complete the activity, please wait for some time. Maybe it's 1 or 2 hours after. Usually it reflects there. Sometimes it reflects there instantly itself. So this is how you to get your certificate. And if you're using the laptop, come to the same page. Just on the right side, you will see there is a go to activity. Just before that, you can see action tab. There is a tab called actions. Once you click on the action tab, you will see the same thing, view completion certificate. This is how to download your certificate, right? I hope all of you have understood. Then just want to tell you something about the domain ID and password. I think you might have received your domain ID and password to your email ID by now. You can just check your mail IDs. Please check your email ID. So we have sent the domain ID and password to your email ID, but please check like that. You might have registered a different mail ID using the Google form, but we have collected your mail IDs from the Google form, and we have collected the default mail IDs from which you have logged into the Google form. So it might be different from whatever you have submitted in the Google form. So we have sent to the domain ID and password to those mail ID automatically collected from the Google form. So you please check your Gmail ID, or yes, your Gmail ID. So if you are not able to see the domain ID and password, you please check your inbox also. Okay, inbox. And if you don't see it in inbox, you please check the spam folder also. You might have received one mail from info@csrbox.org, right? And first of all, we request all of you not to change your password. Please do not change your password, because once you change the password, the thing is like that most of you, you don't save it somewhere, you don't note it somewhere down. So probably it's like that you forgot it, and it's a bit of problem for us to change again. So I'm sorry, there is a spelling mistake here. So please do not change the password over here. Okay. So once you get the password, then we have already given you a link, mail.sbcsrbox.com. It is already given in the mail. So you please log in with that domain ID and password into this mailbox, right? And once you log in, then again there is another link. There is another link given for you to the IBM Skillsbuild platform registration. So please complete the registration activity with the new email ID, new domain ID, and the password you have received. And then you please complete the rest of the deliverables. Okay, so actually you have to complete 3 deliverables. So we request all of you to complete the deliverables. Second, use generative AI for software development and build an agent using the domain ID and password, right? So you can complete the second one by tomorrow and the third one by the 8th. Okay, I mean, please, please don't sit at one time and finish it. It takes a lot of time because it's a 6-hour course. So we request all of you to finish it in one day, because the first 2 courses takes only 1 hour and the last one takes around 3 hours. Okay, so please complete it by taking your own time. It says these are self-paced activities, so it is easy for you to complete at any time. But please make sure that you will submit your final one by 28th February, and you have a project in the second week. So please complete all your self-learning activities in the first week itself. Okay, so this is how your mailbox look like. You can see you might have received a mail from info@csrbox.org. It mentioned domain ID, IBM Skillsbuild Cloud Bootcamp 2026. This is a subject line, and this is how it will look like. Dear, then your name, congratulations, you have been awarded a domain password key. So rest of the instructions are given in that mail. So we request all of you to follow the same thing. And please do not change the password, right? Yeah. Then if you have any other doubts before changing the password, or sorry, before changing or before, if you are facing any troubles for logging into the IBM Skillsbuild platform or any other questions, please use the query form. We have shared the link in the group, and we have already received many students, many queries from the students. So we'll be answering them soon. For some of the queries we have already responded. So please wait, we will answer as soon as possible. So please use the query form. Right. Now, yes. So before moving to the attendance, let me show you. Right. This is how the mail.sbcsrbox.com look like. Okay, here you just need to paste your domain ID and password, whatever you have received, you just need to enter it here. Okay, so please use that. Please, this is how the outlook of the mail.sbcsrbox.com. So I just want to convey this information to you. I will share the details again in the WhatsApp group, how to log in and everything. So if you have any queries, still I would request everyone to use the query form before opening the or before logging to the mail.csr box and completing the registration. All right. So that's it for the day, guys. So I request all of you to punch your attendance. We'll be sharing the details on the screen in your WhatsApp. So those who are able to use the QR code, please punch it using your this QR code. Please mark your attendance using this QR code. We will also share the attendance link in your WhatsApp groups. All right. Thank you so much, guys. See you on next day. So we will have our next class on 26th. We'll be having our the second master class on 26th February. Thank you so much, students. Thank you so much for joining. We'll see you next day.